All right. Good morning. We are going to talk about rational functions some more. All right. So a rational function, we know, are quotients, which means division of polynomial functions. This means that a rational function can be expressed as f of x equals some numerator, some polynomial on top, divided by q of x, some polynomial on bottom, where p and q are polynomial functions. And of course, q of x can never equal 0. So, to do domain of a rational function, we have already done this. We say, Mr. Denominator, you can never equal 0. And that will help us find our denominator. All right, so it says find the domain of each rational function. So what you do is you say, Mr. Denominator, you may never equal 0. And solve it. Add 9. X squared equals 9. Square root. X can never equal plus or minus 3. Now, what that means is they're going to do two ways to answer this. One way to answer it is to tell what can't be in your domain. So one way to express your domain is that x can be everything except for plus or minus 3. That's one way to say it. The other way to say it is in what we call interval notation. And in interval notation, what you do is you say at positive 3 and at negative 3, the function doesn't exist because those values have to be excluded from the domain. But those are the only values that have to be excluded from the domain. My domain can be everywhere else except for negative 3 and positive 3. So to describe my domain in interval notation, we say that this goes from negative infinity to negative 3, jumps negative 3, and it continues from negative 3 to 3. It jumps 3, and it continues 3 to infinity. So to say that, we go round bracket, negative infinity to negative 3, round bracket because you can't include that. To say the jump, we say union, and then we describe this section, which is negative 3 to 3, union for this jump, and then we describe this section, which is 3 to infinity. And I'm not sure whether Math Excel is going to ask you for telling you what the domain can't be or describing the domain of what it can be. Okay? It's saying the same thing but in a different way. This way just tells you what x can't be. This way tells you what x can be. X can be anything in these intervals. It just can't be negative 3 or positive 3. So that's interval notation. Okay? And if you look at the picture, you do not have to graph at this point, but if you look at the picture, at negative 3 there's a jump, and at positive 3 there's a jump. There will be no graph there. There's your boomerangs, and it's got that cubic function in the middle. Alright, so if we look at this one, alright, I say, wait, did we skip one? Where's B? Where's A? Guess I skipped A. Okay, so for C, alright, if I say Mr. Denominator, you may never equal 0, and I try and solve this, alright, I would minus 9, x squared can never equal negative 9, square root, x can never equal plus or minus 3i. Well, what this says is that the only thing that would make my denominator go to 0 is something that is imaginary. In other words, nothing real will affect my domain, so there is no drama, which means my domain is all real numbers. And in interval notation, if you graph that, x can be anything, which means it can go from negative infinity to infinity and there's no jumps. So again, you can describe it this way. Domain is all real numbers. In interval notation, you would say it goes from negative infinity to infinity. And if you can see this, this is not a very good picture of the graph because I need a better window, but there's no jumps, there's no drama, there's no gaps. All right, so yeah, here we go. I changed the window so you can see it a little better. Here's what it's actually doing, and you can see there's no jumps, there's no breaks in it, so that means that there was nothing in my denominator to make the graph jump. All right, so you try this one. Come back when you're ready. And hopefully you got number 3. If not, you say, Mr. Denominator, you may never equal 0. And then we use the zero product property, which says that neither of the factors can equal 0. So this would say minus 5, x can never equal negative 5. Minus 3, x can never equal negative 3. And that's how they wrote their answer. This notation just says the set of all x such that. That's how you read this part. And it's all of the x's except x can never be negative 5 and x can never be negative 3. That's one way to write it. Okay, the other way to write it is an interval notation. And at negative 5 and at negative 3, you're going to have jumps, which means everywhere except there, domain works. So if you were describing it in interval notation, that goes from negative infinity to negative 5, jump, negative 5 to negative 3, jump, negative 3 to infinity. So if we write that, square round bracket, negative infinity, comma, negative 5, round because it's not included, union for the jump, negative 5 to negative 3, union for the jump, negative 3 to infinity. Again, this is how they actually wrote it, but again, I don't know what Math Excel is going to do. They might want you to do interval notation. Okay? And if you look at negative 5 and at negative 3, there's a jump. There must be something in between there, down or above, high or low. All right, so try this one. Come back when you're ready. And hopefully you get, come on, number 2. All right, so I say, Mr. Denominator, you may never equal 0. And I factor that, GCF times what's left, because it's only 2 terms. I can factor out an x. That would leave x minus 4. Then I say each factor can equal 0, so x can never equal 0, and x minus 4 can never equal 0. This one's done. This one, add 4, x can never equal 4. So if I set it up in their notation, it's my domain is the set of all x such that x can never equal 0 and x can never equal 4. If you do it in interval notation, at 0 and at 4 you're going to have jumps, which means everywhere else you can have, everything else works except for 0 and 4. So that would be negative infinity to 0, 0 to 4, 4 to infinity, and these are your jumps. Which means my domain in interval notation goes from negative infinity to 0, union, 0 to 4, union, 4 to infinity. Okay? Alright, and you can see on the graph at 0 there's a jump, and at 4 there's a jump. Alright, you do this one, come back when you're ready. And hopefully you got 3. You say, Mr. Denominator, you may never equal 0. To solve that, I'm going to minus 64, minus 64. I get x squared can never equal negative 64. Square root, and x can never equal plus or minus 8i. So the only restrictions aren't even real, which means there's no drama, which means my domain is all real numbers. In interval notation, you would say negative infinity to infinity. All right. So how do you find the domain of a rational function? Just that first part is you say, Mr. Denominator, you may never equal 0. and you solve it. Now, how do you find the vertical asymptotes and holes or discontinuities? That's what we're going to talk about next. Okay, so a vertical asymptote of a rational function. Okay, if we look again at the graph of f of x equals 1 over x squared, the curve approaches but not, oh my goodness, I can't read. The curve approaches but does not touch the y-axis. The y-axis, which is the line x equals 0, is said to be, x equals 0, it's a vertical line, is said to be a vertical asymptote of the graph. A rational function may have no vertical asymptotes, one vertical asymptote, or several vertical asymptotes. And basically, guys, when we were finding domain, what you do when you find your domain and you find what x can't be, everywhere x can't be, like I was showing you earlier, you have this jump. You have this gap that it jumps over. And there's probably another boomerang somewhere over here. Okay, but they're just showing you one of them. But again, I've kind of been cheating and showing you when you get to those values that your domain can't be, your graph jumps. And those places that it jumps are called the vertical asymptotes. So everywhere you get a denominator equal to 0, what you end up with is a jump in your graph. Okay? Now, we're going to have to describe our end behavior. So what we do is we say as x approaches A from the positive side. Here's this vertical asymptote. Here's the left side and here's the right side. And what this says is as x approaches A from the right. That's what that little positive means. So if I trace my function from the right and I get closer on the right-hand side of that asymptote, the arrow is pointing up. So we say that the function is going to infinity. Okay? And again, on the left side, if we say as x approaches A from the left, so now I'm tracing it this way, and I look at the arrow on the left side of that line, it's pointing up, so we say the function is going to infinity. In the next example, here's the left side of the asymptote, the right side of the asymptote. This says as x approaches A, which is this line, from the right, so if I'm tracing from the right, this arrow on the right-hand side of this asymptote is pointing down, so we say the function is going to negative infinity. And in the last example, here's my A asymptote. Here's the left side, the right side. This says as x approaches A from the left, so if I'm tracing from the left, and on the left-hand side of the asymptote, that arrow is pointing down, so we say the function is heading to negative infinity. Alright, so here we go. It says find the vertical asymptotes, if any, of the graph of each rational function. So to find my vertical asymptotes, we say, Mr. Denominator, when you do equal 0, I'm going to get these vertical asymptotes. So add 9, x squared equals 9, square root, x equals plus or minus 3. Which means I'm going to get a vertical asymptote at x equals 3 and at x equals negative 3. And you're done. That's all it wants to know. That's where my vertical asymptotes are going to be. But again, I think you guys do better if you see a visual. We're going to learn how to graph these later, but for now, just look at the graph of it, and you can see at negative 3, there's a jump in the graph. That's a vertical asymptote. And over here, it approaches 3. Okay? So now let's practice doing our limits. It doesn't really ask me to, but we're going to do this limit stuff. So we've got the limit. The limit as x approaches negative infinity. So as I'm going towards negative infinity, that's here, the arrow closest to negative infinity is getting closer and closer and closer to this horizontal asymptote, but it's never going to touch it. So we say that the function is getting closer and closer to that black line, which is y equals 0. So we say the function is getting close to 0. If we do the limit as x approaches positive infinity, that means I'm looking over here, and the arrow closest to positive infinity, again, is getting closer and closer to that black line. So we say the function is approaching 0. Now we have to do our asymptote limits. Okay, so I'm going to look at this red one first. Okay, and here's the left side and here's the right side. So I say the limit as x approaches -3 from the left. Okay, so here's the left side of x equals -3, and the arrow on closest on the right side is pointing down. So we say the function is going to -infinity. If I do the right side, the limit as x approaches -3 from the right, here's my x equals -3, here's the right-hand side, the arrow closest to the right-hand side is pointing up, so we say the function is getting closer to infinity. And then I've got one more asymptote to do. I'm going to make it green. Here's the left side, here's the right side, so I say the limit as x approaches 3 from the left. So here's the left side of x equals 3. The arrow on the left-hand side of the green line is pointing down, so we say the function is getting closer to -infinity. And then the limit as x approaches 3 from the right, here's the right side of x equals 3. The arrow closest to the right-hand side is pointing up, so we say the function is approaching infinity. And that's how you describe your end behavior, or your asymptote behavior. Alright, so let's try this one. So we have, to find my vertical asymptotes, I set my denominator equal to 0 and I solve it. Didn't we just do this one? I just did this one, didn't I? Oh, same denominator. Oh, I know. Okay, so we have vertical asymptotes of the graph of each rational function. So again, plus 9, I get x squared equals 9. Square root, x equals plus or minus 3. So at plus or minus 3, I'm going to get vertical asymptotes. But, actually, here's what's interesting that happens. I have a vertical asymptote at x equals 3 and at x equals -3. Or I have a hole. So is it a vertical asymptote or is it a hole? How do we know? Well, and I'm not supposed to show you this yet, but I'm going to because you know I like to cheat. If I simplify this, okay, I can't factor the top, but I can factor the bottom. That's going to be x plus 3 times x minus 3. And you notice that the x plus 3's cancel, which would leave me 1 over x minus 3. What that means is, you see how the x plus 3 canceled out? That means that when x equals -3, that's actually not going, and this one would be when x equals 3, right? Because this one canceled, that one's going to be a hole, and this one, since it didn't cancel, is going to be an asymptote. So my vertical asymptote is at x equals 3, and the hole is going to be at x equals -3. Okay? And again, to look at the graph, you see at positive 3, there's actually an actual jump. Okay? It doesn't touch there. At -3, there's a little hole. Now, guys, if you graphed this on your graphing calculator, you're not going to see that hole there. The pixels and the technology just isn't advanced enough to show those holes. But I promise you, even though you can't see it with the naked eye, if you went to the table of values at -3 in the x column and the y column, you're going to get an error. Okay, the function can't exist there. It has to jump over it. It can't touch it. Okay, but if that factor is one that actually cancels out, it's going to make a hole instead of an asymptote, whereas this one didn't cancel, so it made a full-blown asymptote. Okay? Alright, so if we do this one to find vertical asymptotes, I say, Mr. Denominator, when u equals 0, I'm going to get jumps. -9, x squared equals -9, square root, x equals plus or minus 3i, which means there are no vertical asymptotes. And if you look at the graph, there's no holes, there's no gaps, it's smooth and continuous. Okay? Alright. You try this one. Come back when you're ready. And hopefully you got a vertical asymptote at never. Because if I say Mr. Denominator equal to 0, subtract 7, I get x squared equals negative 7. Square root, x equals plus or minus the square root of 7i. Since they're imaginary, there are no vertical asymptotes. And if you can see the graph, there's no jumps, there's no breaks, it's smooth and continuous. Okay, do this one, hit pause, come back when you're ready, and hopefully you got x equals 6 and x equals 4. And what you do is you say, Mr. Denominator, when u equals 0, I will get, you can't equal 0, so when you do equal 0, I'm going to get breaks or jumps or asymptotes. So this should be an easy factor, x times x. Factors of 24 that make 10 would be 6 and 4. C is positive, so they both get the middle, which says at x equals 6, I'm going to get an asymptote, and at x equals 4, I'm going to get an asymptote. Don't just put 6 and 4. These are asymptotes. They're vertical lines. They are equations. They're not just numbers. Alright, and you can always look at the graph and tell, there's my jump at 4, there's my jump at 6. Okay? Alright, so now how do you identify the vertical asymptotes or holes? Well, you're going to get vertical asymptotes when your denominator equals 0. And you're going to get a hole if the factor cancels. Okay? Alright, so now we're going to talk about a value where the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. So now they're going to get around to telling you about the hole that I already told you about. And so like I said, you would say x minus 2 equals 0, which would give me a vertical asymptote at x equals 2, unless it canceled with something on top. And they factored the top into x plus 2 times x minus 2. And do you see how that canceled? And what that means is, instead of it being an asymptote, it's just going to be a hole. Okay? And if you see, if you graphed this on a graphing calculator, what you're going to see is just a straight line. You won't see the hole there, but I promise, it's there. If you went to the table and went to 2 in the x column, you're going to get an error message in the y column. Okay, so horizontal asymptotes. Horizontal asymptotes are these horizontal lines that a function will approach, but usually doesn't cross. Usually. You can't cross vertical asymptotes. You can't touch it. You'll burn up and die. You can't touch a vertical. But it is possible actually to cross a horizontal asymptote, like in this example. This one actually crossed over. Most of the time they won't cross over horizontal asymptotes, but it's not a law like it is in vertical asymptotes. You can actually cross over a horizontal asymptote. Okay, and again, as far as your limits go, this one, if you looked, as x approached infinity, so here's infinity, the arrow closest to it is getting closer and closer to this horizontal line. So we say the function is approaching whatever that value is. They're calling it b, but like if that was 3, it'd be 3. If that was 10, it'd be 10, whatever. Okay? Again, here, as x approaches infinity, here's infinity. The arrow closest to it is really, really close to this dotted line, which is a value of b. So again, we would say as x approaches infinity, the function is approaching b. And same thing on this side. Yeah? If you did it the other way, on this one, if you did as x approaches negative infinity, okay, then if you took the limit, as x approaches negative infinity, this is negative infinity, the arrow closest to negative infinity is pointing down, we would say that the function approaches negative infinity. This one we would say as the limit as x approaches negative infinity. So if I'm going this way to negative infinity, the arrow closest to negative infinity is this one, and it's pointing up, so I would say the function approaches infinity. And same with this one. Here's infinity, The arrow closest to infinity is pointing up, so we would say the limit as x approaches negative infinity, the function approaches infinity. Okay, so now how do you find these horizontal asymptotes? Vertical asymptotes, you set denominator equal to 0. Horizontal asymptotes, you look at the degrees, okay? N is representing the highest degree on top. M represents the highest degree on bottom. If the top degree is smaller than the bottom degree, then I promise your horizontal asymptotes at y equals 0, which on an axis is the x-axis. That would be your horizontal asymptote. If the top degree equals the bottom degree, then y equals TLC, which is the top leading coefficient, the number touching the highest degree on top, divided by the BLC, which I call the bottom leading coefficient, which would be whatever's touching the highest degree on bottom. You would divide those out, and that would be your horizontal asymptote. Now, if the top degree is bigger than the bottom degree, then there is no horizontal asymptote. There will be what we call an oblique asymptote or a slant asymptote, okay, but we won't deal with that right now. Right now, if the top is bigger than the bottom, you just say that there's no horizontal asymptote. So it says, find the horizontal asymptote, if there is one, of the graph of each rational function. To find horizontal asymptotes, we look at degrees. My top degree is 1. My bottom degree is 2. So my top degree is smaller than my bottom degree, which means my horizontal asymptote is going to be at y equals 0. And if you look at this, here's the horizontal asymptote y equals 0. Now it does actually cross it, but do you see that this function will get closer and closer to it but never touch it? And on this end it'll get closer and closer but never touch it. And that's why they actually call a horizontal asymptote its end behavior asymptote, because notice the ends will follow the end asymptote, the horizontal asymptote. If I was describing the end behavior of this, I would say the limit as x approaches negative infinity. Here's negative infinity. The arrow closest to it is approaching this dotted line. So we would say that the function is getting closer and closer to 0. And on this end, the limit as x approaches positive infinity is this way. This arrow is getting closer and closer to this dotted line, so we say the function is approaching 0. Alright, so if we look at this one, my top degree is 2. My bottom degree is 2. Since they're equal, my horizontal asymptote is at y equals TLC divided by BLC. The top leading coefficient divided by the bottom leading coefficient. And so I would get y equals 2 is my horizontal asymptote. Okay, and if you look at the graph, here's my y equals 2. Notice that as I go to negative infinity, my arrow is getting closer and closer to 2. And as I go to positive infinity, my arrow is getting closer and closer to 2. So we would say the limit as x approaches negative infinity, the function is getting closer and closer to my horizontal asymptote, which has a value of 2. And the limit as x approaches positive infinity, my function, again, is getting closer and closer to this dotted line, which is 2. Okay? Alright, so if we look at this one, my top degree is 3. My bottom degree is 2. Since my top degree is bigger than my bottom degree, there is no horizontal asymptote. Okay? And if we look at the graph, you can see, okay, there's no horizontal asymptote. This thing's it's not approaching any horizontal line. It's gonna keep on going up and keep on going down forever. So to do end behavior, we would say the limit as x approaches negative infinity. Here's negative infinity. This arrow closest to negative infinity is pointing down, so we say the function is heading to negative infinity. We take the limit as x approaches positive infinity. So So here's positive infinity. That arrow closest to positive infinity is pointing up, so we say the function is going to infinity. Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got y equals 0. Because my top degree is 1, my bottom degree is 2. Top degree smaller than bottom degree means y equals 0. And you can tell from the picture that this side is getting closer and closer to 0, and this side is getting closer and closer to 0. Alright, try this one, hit pause, come back when you're ready. And hopefully you got no horizontal asymptote, because my top degree is 3, my bottom degree is 2. Top degree bigger than bottom degree means no horizontal asymptote. Alright, and if you look at the graph, there's actually going to be a slant asymptote, okay, that it's following, and that's a line, but we'll get into those later. Alright, find the horizontal asymptote here, hit pause, come back when you're ready, and hopefully you got y equals negative 4/5. My top degree is 1, my bottom degree is 1, so since they're equal, my horizontal asymptote is top leading coefficient divided by bottom leading coefficient, and I can't reduce, so that's my horizontal asymptote. Okay, which is like at negative 0.8, and you can see it's almost at negative 1 there. Alright, so how do you determine the horizontal asymptote of a rational function? Well, if the top degree is smaller than the bottom degree, then y equals 0. If your top degree is equal to your bottom degree, then y equals TLC divided by BLC. And if your top degree is bigger than your bottom degree, then there is no horizontal asymptote. When will there be an oblique asymptote of a rational function, and how do you find it? We really haven't talked about that yet, so I don't know why I started. But there's going to be an oblique asymptote when the top degree is bigger than the bottom degree. And to find it, you do long division. And the quotient, no remainder, just the quotient part. You'll get a remainder, and that's fine. But the quotient is the slant asymptote. And we'll talk about that tomorrow, I'm sure. Alright, so we are at homework, which means we are done for today. So happy homeworking, and I'll see you next time.